You know exactly what I'm talking about. Those little plastic stars stuck to a bedroom ceiling, you flip off the lights, and bam! Suddenly you've got your own private galaxy. It really does feel like magic, doesn't it? Well, what's really going on is actually a super fascinating bit of quantum physics. So, how in the world do they work? How can some plastic star just soak up light and then, just let it out slowly over time? Let's dive in, because I promise you, the real answer is way cooler than you might think.
Okay, so to understand that awesome green glow, we have to shrink way down. We're talking about looking inside the atoms of the material itself, because the secret isn't in the whole atom, but in its tiniest parts, the electrons. I want you to imagine that an electron's path around a nucleus is kind of like a rung on a ladder. In its normal, everyday state, the electron is just hanging out on the bottom rung. We call this the ground state. It's totally stable, totally low energy, just chilling. But then, you turn on a lamp. When a little packet of light energy, what's called a photon, slams into that electron, the electron absorbs all that energy, and it uses that jolt to leap up to a higher rung on our ladder. It's now in what we call an excited state. And this right here is literally how you charge a glow-in-the-dark object.
Now here is where things get really interesting. See, electrons do not like being in that high-energy, excited state. They always want to fall back down to their comfy ground state. But how they fall back down is the entire secret. It's the difference between something that glows for a split second and something that glows for hours.
So, on one side you've got fluorescence. Perfect example is a highlighter under a black light. Its electrons fall back down instantly, so the glow stops the very second you turn the light off. But our glow-in-the-dark stars? They use something called phosphorescence, and in this case, the electrons get temporarily trapped. This little trap is the whole secret. It forces a slow, steady release of light that we see over a long time.
So this quantum trapdoor has a proper name, of course. It's called a metastable state, and you can think of it as a holding pattern for the electron. The electron desperately wants to fall, but the quantum rules of that specific atom create a sort of obstacle course, forcing it to wait. And it's that slow, patient escape that we see as a long-lasting glow.
And you know what? The materials we use to make this happen have gotten so much better. If you had glow-in-the-dark toys back in the 90s, they were almost certainly made of zinc sulfide. And yeah, they'd glow, but they faded pretty fast, right? Maybe 15 minutes tops. But modern materials use something called strontium aluminate, and it is a total game changer. This stuff can glow for hours, and the difference is just huge. Strontium aluminate isn't just longer lasting, it's about 10 times brighter. That's exactly why the glow on a new watch dial or an emergency sign is so much more intense than those old ceiling stars. Its electron trap is just way more efficient.
Pretty cool, huh? But look, you don't have to just take my word for any of this. You can actually see this quantum mechanics stuff for yourself with a super simple experiment you can do right at home.
All right, here's what you do. First, take your favorite glow-in-the-dark object into a completely dark room and just wait for its glow to fade all the way down. Once it's dark, shine a red light, like from a laser pointer or a flashlight, on it for about 10 seconds. Then, you're going to do the exact same thing but with a blue or UV light. So what happens when you use the red light? You turn it off and you see nothing. Zilch. The object doesn't glow at all. It's like you didn't do a thing to it.
But now for the blue light. You shine it for 10 seconds, you turn it off, and voila, you get a bright, strong glow. So what is going on here? Why does one color work and the other one just completely fails?
Well, the answer comes down to one thing: energy. Think of it like this. Red light has really low energy. It's like you're gently tossing ping pong balls at those electrons. There's just not enough oomph to knock them up to that higher energy rung. But blue and UV light, they're high energy. That's like throwing baseballs. They have more than enough force to kick those electrons up into that excited state and charge up the glow.
So this is way more than just a cool trick for toys. This whole quantum phenomenon has some incredibly important, even life-saving applications out there in the real world.
Ever notice those strips on the floor of an airplane? Well, in planes and even submarines, they use phosphorescent strips to line the floors. If the power completely fails and it's pitch black, these strips glow brightly enough to guide people to the exits. No batteries, no electricity needed. And get this, before we had digital sensors, old-school X-ray screens actually used a layer of phosphors to capture the image from the radiation.
So the next time you see a watch dial glowing in the dark, or you catch a glimpse of one of those stars on a ceiling, just stop and remember what you're really seeing. You are literally watching billions of tiny electrons slowly escaping a quantum trap, releasing the sunlight they ate for lunch. It's not magic at all. It's a tiny, beautiful quantum drama playing out all around us.